new insights into the Earth's formation. This is by Arian Bastani, ETH Zurich on phys.org. Although the Earth has long been studied in detail, some fundamental questions still have to be answered. One of them concerns the formation of our planet, about whose beginnings researchers are still unclear. Everything is still theoretical. An international research team led by ETH Zurich and the National Center of Competence in Research Planets is now proposing a new answer to this question based on laboratory experiments and computer simulations. The researchers have published their study in the journal Nature Astronomy. An inexplicable discrepancy. The prevailing theory in astrophysics and cosmochemistry is that the Earth formed from chondritic asteroids. These are relatively small, simple blocks of rock and metal that formed early in our solar system. This is what the study lead author explains, Paolo Sossi, professor of experimental planetology at ETH Zurich. He says the problem with this theory is that no mixture of these chondrites can explain the exact composition of the Earth, which is much poorer in light, violet elements, such as hydrogen and helium, that we would have expected, he says. Various hypotheses have been put forward over the years to explain this discrepancy. For example, it was postulated that the collisions of the objects that later formed the Earth generated enormous amounts of heat. This vaporized the light elements, leaving the planet in its current composition. However, Sossi is convinced that these theories are rendered implausible as soon as you measure the isotopic composition of the Earth's different elements. He says the isotopes of a chemical element all have the same number of protons, albeit different numbers of neutrons. Isotopes with fewer neutrons are lighter and should therefore be able to escape more easily. If the theory of vaporization by heating were correct, we would find fewer of these light isotopes on Earth today than in the original chondrites. But that is precisely what the isotope measurements do not show, he says. A cosmic melting pot. Sossi's team therefore looked for another solution. Dynamic models with which we simulate the formation of planets show that the planets in our solar system formed progressively. Small grains grew over time into kilometer-sized planetismals by accumulating more and more material through their gravitational pull, Sossi says. Similar to chondrites, planetismals are also small bodies of rock and metal. But unlike chondrites, they have been heated sufficiently to differentiate into metallic core and a rocky mantle. What is more, planetismals that formed in different areas around the young sun or at different times can have very different chemical compositions, Sossi said. The question now is whether the random combination of different planetismals actually result in a composition that matches that of our Earth. To find out, the team ran simulations in which thousands of planetismals collided with one another in the early solar system. The models were designed in such a way that over time, celestial bodies were reproduced that correspond to the four rocky planets, Mercury, Venus, Earth, and Mars. The simulations show that a mixture of many different planetismals could actually lead to the Earth's effective composition, and what's more, Earth's composition is even the most statistically likely outcome of these simulations. A blueprint for other planets. Even though we had suspected it, we still found this result very remarkable, Sossi says. We now not only have the mechanism that better explains the formation of the Earth, but we also have a reference to explain the formation of other rocky planets, the researcher says. The mechanism could be used for explaining, for example, to predict how Mercury's composition differs from that of other rocky planets, or how rocky exoplanets of other stars might be composed. Our study shows how important it is to consider both the dynamics and the chemistry when trying to understand planetary formations, Sossi notes. He says, I hope that our findings will lead to closer collaboration between researchers in these two fields. This was provided by ETH Zurich on phys.org. Please leave your comments and thank you for your support. kindly support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.